page up, page down, or arrows, and you're all set. Let's give him a hand. Thank you very much for coming, Ed. I really appreciate it.
I'm going to go down a little bit of a different route from what you're used to seeing in the molten salt reactor community. I decided that the best way to go to get the most flexibility and most safely and get something done today is actually to build a fast reactor rather than a thermal molten salt reactor. Yes, that's a little bit different, and I'm going to go over why that might be all right. So my name is Ed Pheil. I'm Chief Technology Officer and co-founder at Elysium Industries. We were operating in Boston for like 2 years. We decided to move our offices back to Schenectady because most of the people that came to join me were from the Naval Reactors program. So a little bit of philosophy up front. How do you achieve disruptive change, disruptive technological change? Basically, you need to believe you can change it. One of the things I was told at the Naval Reactors program is, you can't do that, or we can't do that type thing. And a lot of it had to do with, we can't get money to change the fuel system to a high temperature fuel system. And I tried to convince them in a molten salt reactor, you don't need to spend all that money for a high temperature fuel system because there's 30 to 50 years of high temperature fuel testing to get a new high temperature solid fuel built. Liquid fueled reactors that are, the fuel is self-repairing, you don't need to go for that long. All right, I couldn't convince them that they should go that route. But I also saw an enormous amount of technology that would allow you to do other things. All right, so my history. I worked at the Knowles Atomic Power Laboratory for 32 years. I operated the MARF prototype, training students to operate that nuclear plant. I worked on 9 different ship classes, so 9 different distinct water reactors. There's the list of all the reactors that I worked on. I did startup testing for 15 reactors. Here again, there's a list of the ones that I've started up. I worked on the Jupiter Icy Moons rocket to go out to Ganymede, Io, and Europa until NASA basically got wagged the other direction on their funding and pulled out of that. One of the presidents said Moon, Mars, and beyond. We were working on beyond, so they started working on Moon. Right? In that time, I was always the go-to person that the CAPL went to if you had to work on a different kind of coolant. They were always looking for a different kind of reactor, right, that was better than the water reactor that they had. That comment about the fuel was one of the key things that always kept them from going that way. But most of the people that were working there were working on water reactors, and they couldn't think outside the water reactor box. I had this knack for being able to think outside that box. So they always called on me. All right, and I mentioned the people followed me out of CAPL to Boston, so we moved our offices back. We have 300 years, design years of experience on our team of actually building, operating, maintaining, actual reactors, and answering questions on the fly with ships at sea even. Just a basic background of what our plant looks like. Our base plant is 1,000 megawatts electric, 40% efficiency approximately. A chloride fuel salt, which is different than most of the ones you're used to, and a fast spectrum neutron flux, so higher fuel loads, what that means. But what it allows you to do is get to fuel flexibility. You can burn depleted uranium, low enriched uranium, spent nuclear fuel, reactor-grade plutonium, weapons-grade plutonium, thorium, and natural uranium. And we consume it basically to 100%. Right? Existing water reactors burn 4%. If you burn the other 96%, that's a factor of 24 times as much energy left in that spent nuclear fuel. We're 25% more efficient because we're 600 C instead of 300 C. Right? So that's 30 times as much just in the spent nuclear fuel. And there's 10 times as much depleted uranium already mined out there. So 30 times the existing plant life for spent nuclear fuel is about 2,000 years. worth of fuel just for the spent fuel. And if you include the DU that's already been mined, that's 10 times that available. There's our core temperatures currently, low operating pressure as all the other molten salt reactors, structural components. This is kind of key. We are using existing nuclear qualified materials in our reactor. We are not going for something that is not already nuclear qualified. There's a lot of work done to get to Hastelloy to get the nuclear qualification. I think it might have ASME qualification, but I'm not sure if it's the actual grade that you would actually use or if it fits within that grade specification. And at this point, we don't want to have a power system that is developmental. So we're not doing supercritical CO2 unless it's actually been proven to be both doable, which it's not yet, and reliable. Because we don't want our power system to cause our reactor to fail. So we're counting on a steam power plant at this point. We might try to squeeze in a gas turbine if we can. So, flexible power. All right, so I said our base reactor was 1,000 megawatts electric. All right, that's 8 loops, compact heat exchangers, as you see there, 8 pumps, 1 pump in each loop, and full flow pumps all the time. Basically, there's going to be 1 large turbine or 8 small turbines. That starts to sound like NuScale, right? NuScale has 1 turbine per reactor plant. We can have 1 turbine per loop if we wish, right? That allows us to scale. Allows, if the 1 turbine goes down, allows you to stay up at power. And I'll get into that later too. But you can scale down. If you go down to 2 loops, that's a quarter of the power, 250 megawatts. If you go down to 2 loops and half the pump flow rate and half the heat exchanger size, it's 125 megawatts. And on down, you can basically the reactor is sized for criticality. It is just barely critical all the time. Right? So there's no scale up, scale down for the reactor because it's just the minimum amount to stay critical. The flow rate through it determines your power rate. Right? And then the heat exchangers that are attached to it and the pumps that are attached to it can be changed out, go up in power and down in power by making the flow rate higher, the pump's bigger, the heat exchangers bigger, or number of loops for that matter. And well, I said superheated steam, but it could be supercritical steam too. The problem with supercritical steam is it increases the cost of the power plant, but in a coal plant, they would go to supercritical steam because it saves them on fuel. Our fuel doesn't really cost anything, so I'm not sure we can justify the supercritical steam cost, the plant cost. Reactor types. The one that I've been showing is the loop plant. The pipes go out of the reactor. Most of the molten salt reactors and most of the small modular reactors use the one on the right, which is an integral plant. The problem I see with the integral plant is you can't do maintenance on it without doing an enormous amount of tear apart to get at components that are lower down. All right? So I like either the loop plant or the modular plant. Now, I'm dating myself here. This is the original definition of modular plant, all right? Where each component is a separate module. The current definition of modular plant means you can ship it down the road as one reactor, which actually is not possible except for liquid-fueled reactors. But I'm not going to go into that here. We can talk afterwards. Right? So I like the modular plant the best. So that's where I prefer to head on that. The loop plant is the easiest one to design, though, today, at least in the United States. Right? Fuel chloride salt chemistry. The fuel salt, the functions of the fuel salt. Solvent for the nuclear fuel. We're going to end up with somewhere in the neighborhood of 30% heavy metal chlorides in our fuel. You need it, right? It's a fast reactor. The cross sections are lower, higher energies, so you need more fissile material. You need more fertile material to convert into fissile to get that. All right? It's the working fluid for transporting the heat out, and it needs to prevent the release of fission products. Most of the fission products, except for xenon, krypton, are chemically bound in the chloride salt. So even if you had a leak, They're chemically bound, they're not going to be released, and you leak it out, it would freeze. That's standard molten salt technology. One of the advantages of the chloride salts, and the reason why Sandia uses it for solar salts, and why Argonne used it for pyroprocessing, is it melts at about 300 degrees C, lower temperatures than fluoride salts of the same composition. All right, and lithium fluoride, beryllium fluoride, I think that's only 70 degrees delta, but chloride salts are still lower. But I wanted to go to chloride salts to get that lower melting point, to get away from needing highly enriched lithium, which is a proliferation problem, because lithium enrichment means you get lithium-6 enrichment, which is a weapons material. So I'm trying to get away from that and the tritium as well. The other advantage is Argonne National Lab already uses standard materials for that. There's a lot of talk about corrosion versus water. Salts are less corrosive than water if they're pure. Don't put salt in water. Don't put water in salt, and you'll be okay. All right? Don't drive your pet car down the road when it's snowy out. That's essentially people preventing putting salt in water on their car. That's one solution, at least. But the corrosion of chloride salts, chloride is less aggressive than fluoride or fluorine, and so it's less corrosive than that, and that's why you can get away with standard materials in using that. That's why Argonne does that. The other advantage is it's better for passive control and active control. We don't have the thermal expansion of graphite with temperature, or the expansion and contraction of graphite over lifetime with irradiation to account for in our temperature coefficients and our void coefficients. We just have a liquid core. There's just a can full of a liquid that's enough to go critical at a certain temperature. And that's it. And so that pretty much guarantees you have a negative temperature coefficient under all conditions. I'm not going to go into detail, but the chloride chemistry, and Kim would probably be able to explain this probably better than I can. The chloride chemistry is such that the electronegativity, the Gibbs free energy of the molecules is such that you can separate out most of the fission products without removing the actinides. So the actinides can be left in the core at all times. So our waste stream is just fission products and some of the carrier salts. But there are a few fission products that don't get pulled out because they're too close to actinides, and we leave those in. Things like cesium and iodine. They actually reduce our melting point of our salt, so that's a good thing. And I'll get into this a little bit later, but one of the reasons for starting up with spent nuclear fuel is it has cesium and iodine in it already, and that helps reduce our starting melting point. A lot of reactors, when you burn in fission products, the melting point goes down with time. We want to start with as low a melting point as you can at the beginning of life. And that but the decrease in melting point allows you to increase your delta T and increase your power rating with time from beginning of life to later in life. But we want to start out the high power from beginning of life. Enhancement of nuclear non-proliferation and safeguards for this. I already talked about that we can remove fission products only. So one of the big deals that the DOE and the NRC has with molten salt reactors is, how do you count the actinides coming out of the reactor? How do you know that somebody hasn't stolen any? In our reactor, we essentially do a mass spec and a Raman spectroscopy and figure out whether there's any actinides in there and what level, but that's less than 1% of the actinides come out from that pulling out, and that's just a process loss. And I expect to be able to get that down much lower with a few other techniques. So the uranium and plutonium always stay mixed. They always stay in the reactor and never come out. The waste stream comes out. We actually reprocess the chloride, recycle the chlorides, I apologize, recycle the chlorides back into the fuel manufacturing process. The fuel manufacturing process takes chlorides to convert spent nuclear fuel oxides into chloride salts in one chemical step, right? But you need the chlorides to do that, so we might as well just recycle the chlorides out of the waste stream back into the fuel manufacture. Since the fuel manufacturing is already radioactive, the chloride's radioactive, no big deal. And oh, by the way, I have somebody that already wants to buy the zirconium off of us too, the radioactive zirconium from spent fuel, because they can't figure out how to get it without somebody using the stuff on the inside. So feed-in starts, so the one fuel option 1 is essentially high-assay, low-enriched uranium, so-called HLEU. It's between 5% and 20%. That's the first option, and it's about 90% fertile, 10% fissile in that case, and it's between 10 and 20% enriched. The feed-in for HLEU, a started-up reactor, is about 20% enriched, and that decreases with life as you burn in more plutonium. The problem with the HLEU is you need to have this high enrichment. But I can't drive an enrichment facility because once I get this reactor going for a few years, I don't need the HLEU anymore. So the enrichment facility is not needed any longer. So I can't drive the long-term development costs of an enrichment facility that can go up to 20%. Okay, second fuel system, plutonium and spent nuclear fuel. We use weapons-grade plutonium, reactor-grade plutonium, and that gets us straight into our normal chemistry, right? We don't have to worry about changing chemistry through life. All right, thorium. Since this is a thorium conference, I thought I'd talk a little bit more about that. Thank you, Jim, for pointing that out. Uranium-233 and thorium. If you look at the two red lines on the first curve, that's the fission cross-sections for that. So yes, in a fast reactor, you have low fission cross-sections, but you can make those work in any of the systems. But you'll notice the reason why this curve is on there is it also has the uranium-238 and the thorium-232 fission cross-sections. So you notice in a fast reactor, which is to the right of that red line is where we're operating, those two cross-sections come up, and for uranium-238, we get about 10% fissions. For thorium, we get about 5% fissions. That's like having a few extra free neutrons. The curve on the right is the number of neutrons per fission that you get. You'll notice the green line on the right where we're operating in the fast spectrum is way higher than the number of neutrons per fission in the thermal spectrum. That makes the neutronics much easier to account for leakage, absorptions, poisons, or fission products in the coolant, right? But you'll notice also that the red dotted line to the right of that red vertical line is actually higher than the thorium, the uranium-233 neutrons per fission. So I can actually run this reactor on a fast spectrum burning uranium-233 and thorium in there. The other thing I can do is I can start it off on plutonium and uranium and breed thorium into 233 in the blanket. I won't go into that. Notional, and only notional, molten chloride salt fast reactor 2. Passive safety, pumps without electricity. I figured that out, how to do that. Haven't done the development. Pumped draining, which means not a freeze seal, and a pump that doesn't need electricity to run, and drain faster than a freeze seal, which is the same thing. I've identified that. This was written earlier. This was just, shall we say, 2 typos or 3 typos in a posting and stuff. Allothanium and stuff. We want to use everything. And we can use everything. We don't want to discharge fuel. We want to minimize proliferations. We want to get to 1300 C or 2400 F, which gives us 60% efficiency in just about any process, heat, temperature, any process you want. 1300 C is, concrete is made at 1400 C. We can get the heat up to 1300 C, and then you use electric heat to get to 1400 C to do concrete type deal. And the last one is don't shut down in a natural disaster. Reactors aren't the problem. It's not danger, right? The danger is people not getting medical care because they don't have electricity. I'll skip the summary because I'm out of time. Okay? Thank you. Nuclear is by far the safest. People die from coal every year. People die from gas every year. People fall off of solar panels every year. People fall off of wind turbines and get electrocuted by working on wind turbines every year. Hydro, the largest deaths from any one plant from a power production is hydro, the Banquillo Dam. Like 127,000 people died. Nobody has died in the public from a nuclear plant. So what does that mean? It means that if you are driving the cost of nuclear plants up to make them safer, when they are already so safe that nobody dies from them, you are preventing nuclear plants from being built. There is no reason to not continue to operate Indian Point. There is no reason to shut it down. You cannot build a new gas plant cost effectively compared to the power produced by Indian Point. So if you want to reduce the death rate in the public, you need to build nuclear plants to displace the more deadly forms of power.
I make radioisotope batteries or portable nuclear power supplies. Radioisotope batteries have the advantage of operating non-stop for the duration of the isotope, which means that these batteries can provide power for up to around 400 years. They also have the advantage of not being pressure or temperature dependent, meaning that they can operate in outer space, inside the human body, like inside a pacemaker, or in high pressures within the deep ocean. Nuclear batteries have been looked at before, but traditionally they use man-made isotopes from our nuclear weapons program. My technology uses isotopes that can be found in spent nuclear fuel. This is important because it drastically reduces the cost while massively increasing the potential efficiency of the devices themselves. For example, traditional radioisotope batteries use man-made plutonium-238. This costs around $90,000 per gram. I'm looking to use isotopes from spent nuclear fuel, which can cost as low as $45 per gram. The current radioisotope batteries actually have an efficiency of around 1 to 6%. I'm hoping to get efficiencies around 30 to 50%. Radioisotope batteries have the advantage in that they last for the duration of the radioisotope. This can be up to 400 years for some materials. I am focusing on the energy conversion mechanism itself rather than the battery design. My conversion mechanism uses a plasma to convert ionizing radiation from any isotope into electricity. This means that I can match the isotope to the industry need and making my battery the most efficient and effective for a given application. As I started to develop this project further, it became readily apparent that I was going to need a large facility to do this work. The Department of Energy invested $500,000 for me to come here to Argonne National Lab in the Chain Reactions program, where I get to use their linear accelerator and develop my proof of principle and prototype here. This drastically cuts down on the product development cycle of my technology, enabling me to get into the market about a decade sooner than I would have on my own. Currently, I'm looking for non-dilutive funding such as government grants, as well as a corporate partnership for someone who could help me develop my prototype and actually begin the manufacturing process on nuclear batteries. My technology is not only more efficient, cost-effective, and the supply of isotopes is abundant, but my technology is also safe.